Organizing committee for the wonderful attention, help, the extraordinary organization of the event, also the scientific committee and the four societies that celebrate the meeting. It's a pleasure to be in Cádiz again. I have many friends. I knew some people before coming to this conference, and Rafa and Jesus, and now many more friends that I have met here from the University of Cádiz. So. The talk is just an overview of different approaches that have been used in the recent years about how to deal with uncertainty through the use of differential equations. Of course, uncertainty can be handled through mathematical models in different ways. This is one of the approaches, but there are others. We have attended to several talks these days about, for example, stochastic differential equations. There are equations with randomness. There are many different ways of handling uncertainty presenting in real phenomena. And in my case, I'm going to speak about differential equations which are defined on spaces that allow to handle uncertainty through the use of fuzzy sets or fuzzy intervals in this case. I'm not going to speak about the n-dimensional case, just fuzzy intervals. So I just, it's quite simple, but I would like to make some overview about the basic concepts, what are the kind of sets that are going to be used. And the idea of the talk is to put into contrast essentially the definition of generalized derivatives for functions which have values on this kind of general sets, and put it in comparison with other approaches, in particular with the case of differential inclusions, which is another way of working with set-valued differential equations, for instance. So I will present I will recall some concepts of general differentiable functions, and I will put into contrast in simple examples, which are very more simple to see the difference between one of the approaches and others. But of course, you can study many nonlinear problems using the same ideas. No? So I'm not going to put a lot of emphasis about all the situations where the uncertainty appears. It is clear that in many real phenomena there are many factors which are imprecise, and many times it is difficult to obtain exactly the data, because we can have, for example, imprecise tools to measure, or just simply because there are many information which is imprecise, not because in terms of probabilistic, not in probabilistic terms, not in random terms, but just in subjective terms. And in relation with this, many linguistic variables exhibit this behavior of the many terms that are uncertain because of, for example, what is the idea of being tall, being beautiful. Many terms and many expressions from the linguistic point of view exhibit this kind of uncertainty based on subjectivity. There are many approaches to define and to study the properties of the solutions to differential equations in these fuzzy spaces we are going to use. One of the first ones, because the idea of fuzzy set goes back to the work of Professor Lofty Thade from 1965, where the concept of fuzzy set is introduced. And since then, many research lines have been developed using fuzzy sets in different contexts. Of course, in the University of Cádiz, there are groups working in this topic. Many other groups in Spain, also in Brazilian groups working with this kind of tools and equations. Subextension principle is quite useful in the sense that allows to work from a deterministic problem and extend to a fuzzy context, but you can use a deterministic solution and then fuzzify the solution. It is a good approach, but in many cases difficult to compute. So Many other different approaches have been proposed. For example, the notions of differentiable functions in this context, and differential inclusions, which are the main I'm going to speak about. I will show you that even for very simple examples of linear problems, very curious particularities appear for this kind of equations. The expected reasonable properties that are obvious in classical problems are not valid anymore in this context, even if we don't work in the fuzzy context, but just with intervals. We can find very different behavior in comparison with what happens with the classical solutions of ordinary differential equations. And I will make some comments about the connections between these two approaches I have mentioned. No? So, of course, there are many fields where these kind of concepts and tools have applications. I have put there some of them: image processing, the study of patterns, optimization, neural networks. There are many fields where you can find applications. So, starting with the first approach I am going to speak about. When one wants to consider a differential equation in a general space where you can allow some kind of uncertainty, you find that the functions are not real valued, but they are set value. So you need first you can think about the definition of a derivative for this kind of function. So the first works about the differentials of functions with fuzzy values can be found in these works by Dubois and Prede and Puri and Relescu for the 82 and 83, and of course the other techniques I have mentioned. And the first works in fuzzy differential equations come from the end of the 80s of the last century. So I will present some ideas about the H difference, or Fukuhara difference, and the corresponding derivative, strongly generalized derivative, and generalized H difference and generalized H differentiability that have been developed by several authors, as I have included there. There are more general concepts of derivatives, and there are still many researchers working on improving these notions, but since I'm going to present examples quite simple, with this notion it is quite easy to see the difference of properties using the different methods. The approach of differential inclusions is connected with many monographs and books, for example, about set valued analysis from Oban and Frankowska or Michelina. And in relation with the fuzzy context, Haller-Meyer in 1997 explores the applicability of this method to equations with uncertainty. There are many other contributions I am not going to explain in detail, and I will just go to the basic definitions about the idea. I am going to call fuzzy set. I'm not going to work in n-dimensional cases, only the fuzzy sets in the real line. This construct is a mapping, which is defined in a base space, which in this case is the real line. It can be any metric space X, with values in 0, 1. Of course, there are other generalizations which allow different range also. But in the picture, you can see a simple example of just a function defined in the real line with values between 0 and 1. Okay. To work with equations that are using elements in this base space, the simple idea is to make cuts of this function and to detect at which point the function has values greater than a certain level. This level is like the level of certainty. I mean, when the function is 0, you understand that these elements in the domain are not representative. They are level of certainty 0. the values where the function is 1, it is what is called the core of the number. This represents the full membership to the fuzzy set. And these are, in this example, between 1 and 2, you find intermediate values, so different levels of certainty between 0 and 1. So, but without a probabilistic distribution behind, in fact. Okay, but when you are considering a differential equation over this kind of elements, and you want to compute, you need to pass to what is called the level sets of the element. So in this example I have drawn here for the beginning, it's not a good example because you see that the interval where the function takes value greater or equal than a certain alpha is not bounded. So we want to work with the endpoints of these intervals. So we need to restrict the type of functions used to define these differential equations. So taking as the alpha level set the elements of the domain with values greater than or equal to alpha, and calling the support the closure of the union of these level sets with alpha positive, that is the closure of the elements where the function is strictly positive, we need to consider, to make a restriction about the hypothesis on this function u. We have to add some properties in order to be able to work with the endpoints of these alpha level sets. So at the end, a differential equation on this space is reduced to make cuts and to study a family of differential equations for each level of certainty. So if you decide you want a level of certainty 1/2, okay, you can consider this level. But in general, we are interested in knowing what is the behavior of the complete set of predictions from alpha equal to 0 to alpha equal to 1. So these are the standard restrictions imposed on this kind of sets in order to be able to work properly with this kind of equation. So the classical space of work is the space of normal, upper semi-continuous, fuzzy convex with compact support functions. With these 4 conditions, we have that the level sets, in the case of the one-dimensional fuzzy sets, that is in this case I am presenting, you have compact intervals. So you can work with the endpoints without problem. So this is these are the restrictions, and with that you get compact, non-empty of course, level sets. That they have some, also some, they are nested. They are nested. Because when your alpha is increasing, the interval is smaller. And the operations can be defined using the fuzzy extension principle. I will put in some moments. But for the case of the addition and the multiplication by scalar, well, it is reduced to the same operation in the intervals, which are the level sets of the fuzzy set. That extension principle allows to extend not only the addition and the multiplication by scalar. You can extend any other function f if you, in fact, you have an f defining the Cartesian product of 2 non-empty sets with values in another non-empty set, and you have you can define the extension of f. This set would be the set of fuzzy sets over x1. I mean, functions defined in x1 with values in 0, 1. Here you have the extension of x2 to the fuzzy context, and here on the right you have the extension of y to the fuzzy context. And with this supremum of the minimum of the values of y1 and y2 in the pre-images of a fixed y, if any, and 0 in other case, you can extend any function to the fuzzy context. Well, restricting our attention to these particular cases and these particular functions defined on the real line with values in 0, 1, with those 4 properties that give the level sets are compact and non-empty, the structure of the space of fuzzy intervals is complete metric space. And then if you have a complete metric space, in general, you can work, you can make have a lot of properties concerning the study of differential equations, the existence of fixed points, and good properties about the behavior of the solutions. So it's a good collection of restrictions in order to impose to a function to be considered as a fuzzy interval. So how can we define a differential equation in this space? There is, the definition of the integral is quite simple. If you have a function defining a compact interval, real interval, with values in this fuzzy space of, we are going to call the space of fuzzy intervals, can be defined level-wise as the integrals of the measurable selections of the cats. I mean, we are proceeding level-wise. This is a Mann integral, and it has quite good properties. In fact, any continuous function in a compact set with values in the set of fuzzy intervals is going to be integrable with this definition. So we can proceed with this concept and define a differential equation. Sorry. Trying to, at the beginning, trying to get something equivalent to what happens in the classical case. In the classical case, we are used that we have a differential equation and we have an integral formulation which is completely equivalent under proper conditions on function f. No? So if you want to define a concept of differentiable function, and you think about the classical notion of derivative, what you need really is a good difference. And the problem that you have with this kind of spaces is that the addition of the opposite is not a proper difference. You cannot use just simply because even in the crisp case is the case where all the levels are the same interval. If you add a non-trivial interval to the opposite of the interval, you don't get 0. So that is the main reason that the addition of the opposite is not a good definition. So the first definition of difference considered is the H difference, which is, well, very easy to construct if it exists, given two, if you want to start with intervals, given two intervals, if there is another interval in the sense that the first one is the addition of B to Z, then you say that the H difference exists. This is a question of the length of the intervals. If you have an interval, to the existence of the H difference is just a question of what is the measure of the intervals. In the fuzzy case, it's not so simple because you have different alphas, so you have to check more properties, especially if you are considering a lot of restrictions on the definition of what is a proper fuzzy set. But considering this difference and assuming it exists, the classical notion of derivative can be extended quite straightforward. The problem is that if you have intervals, the existence of the H difference is going to depend on the length of these intervals. So more cases appear in the sense that you can consider, the red is not working very well, you can consider differences where you are taking values of the variable always, the first one always on the right, or the first one always on the left, and you can mix. So at first you have four different cases. By distinguishing these four cases, you have four notions of differentiability, which this one is called the H or Fukuhara differentiability, and if we consider the four different cases, we have the notion which is called the strongly generalized differentiability. It is not the more general. I will show you more general definitions, but just to illustrate with some linear problems, very simple linear problems, this is the H difference, and the H differentiability is not a good notion for differentiability in the sense that there are too many restrictions on the type of solutions you are going to obtain. If you consider a linear problem, very simple linear problem of this type, this is a crisp problem with crisp initial condition also. The first definition that considers the value of the function on elements which are on the right at the point first, is always going to give solutions that increase the diameter. I mean, the diameter of the level sets are going to be always monotonic increasing. That is a big problem because when modeling some real phenomena, it could happen that this diameter, it comes a point where it is too big and is not representing properly the properties of the phenomena itself. So in this case, in green, it is shown the diameter of the solution, which in this case, it is not a very bad situation because it's bounded. But a simple modification of a linear problem of this type, when we are working with intervals or fuzzy intervals, produce that the behavior, the qualitative behavior of the solutions change in a very important way just by making slight modifications of the problem. I mean, if we consider a problem where this term is passed to the other side, just think about the classical case. Just imagine we can pass this term to the other side like minus 3u. It is not possible to do it in this case. But if we do that, the midpoint of the solution is going to be preserved, but the diameter not. And doing that, you see that in this case, the diameter is not going to be bounded. So H differentiability is not a good definition. Okay, so these are the other two cases where they mix the properties of 1 and 2 differentiability on one side and the other side. These cases correspond with the existence of what is called a switching point. When you have a solution made by pieces, and in some sense you pass from a part which is 1 differentiable to another which is 2 differentiable, then we call one type of switching point, or the reverse situation, when you pass from 2 to 1. Okay, that's the notion of switching point. In a switching point, you are assuming that the function is differentiable on both sides, and the limit of the derivatives, the one-side derivatives, have to exist as a fuzzy number. In the linear case, the introduction of switching points allow to work with, for example, with periodic phenomena. So about this comparison between the properties of the solutions from the point of view of differentiable solutions of the differential equation using a notion of derivative, the obtention of periodic solutions is a quite difficult task, because one of the cases of the definition provides solutions that increase in length. The diameter of the level sets are increasing, and with the other types are decreasing. Okay, but we are not going to have, at the same stage, one solution that is going to be periodic. This is another problem that will be solved using differential inclusions. If we want to have a periodic solution to just a linear problem of this type, we can do it by changing by pieces, constructing a solution by pieces, adding parts where the solution is 1 differentiable to parts where the solution is 2 differentiable. In this case, you are able to construct a solution that increases the length, decreases the length, and at the end, you are able to construct a function which is periodic. That, without the switching points, is completely impossible. So, periodicity is another reason that supports that the approach of differential inclusion is going to be better than using a notion of the differential of fuzzy function. No? We have studied some periodic problems using the strongly generalized differentiability, but it is not so useful, and it was tricky to write expressions of the solution using this approach. So this is one of the reasons, another reason that supports the use of alternative approaches to the study of these equations. Here we have put some problems. In the first one, we are passing using an interval where we have the one solution, and some of the levels are included here, of course. not all, the support and the core in the middle. And this is the part, in this interval, the solution is one differentiable. And starting at this part, you see there is a peak here because it's a change of differentiability, it's a switching point. We have two differentiable solution, and in this case, for this function, is made reversely. In the linear case, it's quite easy to make this construction because the coefficient a of t, the study of the change of the sign of the coefficient a of t is helpful to construct the different type of solutions, one or two solutions. In any case, it is not easy to write the explicit expression of the solution just for simple problems of this type. Another drawback of studying these equations from the notion of some generalized differentiability is that in the classical case, of course, these three problems that are written here are completely equivalent because the terms pass from one side to the other without problem. As we have mentioned, this is not possible anymore in the fuzzy case. So just to handle with these three simple, very simple problems present a lot of difficulties in the obtainment of the solution because they are not equivalent. So this is another reason to try to look for another approach that solves this situation. We have calculated explicitly these solutions in several works. A collection of properties about how the generalized derivatives behave in relation with the operation is another of the reasons that suggest that we have to consider a more general approach. If you think about the algebra of the derivatives, how you can operate with differentiable functions under these concepts defined, the addition of two fuzzy functions, for example, if they are differentiable with the same case, it is easy to prove that the addition is also differentiable from the same point of view. This is a result proved by Bede, Rudas, and Benzik in 2005. And if we change here this hypothesis and, for example, try to prove a similar result, assuming that f and g are differentiable from under different cases, the expression expected for the derivative of the sum can be really different. Also for the product, for example, of a real function times a fuzzy function. So the derivative of the operation between fuzzy functions, if you consider notions of, for example, a strongly generalized differentiability, the expressions obtained are not very useful to handle in general, and produces that the expressions of the explicit solutions, even for simple cases, they're so intricate. We have extended some of these properties. For example, for the case of the sum, we can show you that if you have two strongly generalized differentiable fuzzy functions, and if you change the type of differentiability in the first and in the second, you need extra conditions in order to guarantee that the addition is going to be differentiable. It's not deduced straightforward. And if we expect to have here that the derivative of the addition is the addition of the derivatives, we don't obtain this expression necessarily. So there are many issues that do not show that this method is not so convenient in order to deal with differential problems, generalized differential problems in this kind of spaces. So you have to distinguish a lot of cases. For the case of the H difference, the variability of the expressions is big when the type of differentiability of each term changes. Additional restrictions have to be imposed. So it is to use this type of properties is is not really helpful to obtain useful solutions to very simple problems. Just to show you the type of the expression of the solution, the general solution of these linear problems which are not equivalent that I showed you before. To unify in a convincing way the different expressions obtained, we have used this notation. We have used a hat difference, which can be sometimes the age difference and other times the addition of the opposite. Assuming this notation, we can obtain a general expression for the solutions to linear problems, which is of this type. It's not very useful because this difference here is the same as here, this one. These terms are the same. Phi is in relation with the linear coefficient A of t. Gamma involves the forcing term and the hyperbolic cosine and hyperbolic sine of this function. And it is so difficult to express because you have to make particular cases of this difference. If you select one of these differences here and here, this has to be the same. You can choose here another type of difference and here another type of difference. So you have many cases written in a uniform way that give way to all the different solutions, but for simple problems. For example, if the coefficient A is negative, this expression can give way to the H solution to the first problem. But it can be also the two solutions to this problem or the one solution to this problem. And these signs on the right mean the asterisk means that you don't have guarantee that the involved difference exists. And these other symbols mean that even if the H difference exists, you don't have guarantee that this expression represents one or two differentiable solutions. So it's not very useful to use this kind of derivatives from this point of view. In this table, we have represented the different selections of the differences in order to get all the solutions to the three problems mentioned. We have not introduced here it seems that another problem is missing, which is all this term on the left-hand side and a zero on the right, but in this case it's a trivial case, only real solution. Okay, so Bede and Stefanini in 2013, they proposed a new difference in order to get a more general class of differentiable functions. And this is the generalized Fukuhara difference, or called generalized H difference, also GH difference. And this difference is defined in the following way. The difference between X and Y exists in under two possible expressions. It could be the H difference of X and Y, that is in the interval case is easy when the length of the diameter of X is bigger or equal than the diameter of Y, or reversing the opposite of Y minus X. This is a more general definition of difference. I have written here for the fuzzy case. If you define it for the interval case, this difference solves one of the problems, one of the difficulties of the previous definition, which is in intervals, this difference always exists. So you don't have to care if you have a differential equation with values in an interval. You don't have to care about the existence of the GH difference, because in this case it's going to exist. But in the fuzzy case, it's not so obvious, because it is not enough that you can calculate these differences level-wise, because at the end you have to recover a fuzzy number, and you have a list of restrictions that they have to be fulfilled. So it is a more general situation with this notion of difference whose level sets have this expression, minimum and maximum. You can define a generalized H differentiable function just with this notion of the limit. Of course, in many cases, I mean, this is an extension of the previous one, in the sense that if you have the same type of difference on the right, at the right of T0, and the same for on a certain interval, and the same kind of difference on a certain interval before T0, you recover the cases, the previous cases, so the solutions under a strongly generalized differentiability are also solutions in this type. What this definition adds is the possibility of, when you are approaching T0, that you don't have the same behavior in all the ages. So this definition allows to have oscillation, and the intervals can increase and decrease the length approaching T0 from both sides. So there are some cases which are considering in this, with this notion of differentiability that are not considered in the previous one. Of course, the solutions you have with the other approach are also solutions from this approach. Another definition of generalized difference could be a level-wise generalized difference, which is you use the GH difference on each level, but for each level fixed, and you don't worry about if all the level differences give way to a fuzzy set under the restriction set. So with this definition, you could change the type of GH difference on each level. So in intervals, the GH difference always exists. So using this, you are extending the class of functions that you can study the differentiability. And another even more general notion of differentiability of fuzzy functions is based on the G difference, just called generalized difference, which is constructed in this way. The alpha level set, for alpha fixed, it is obtained as the closure of the union of the GH difference of the levels with beta greater than or equal to alpha. The advantage of this difference is that here you have solved the problem of the existence. You can guarantee that always this kind of difference is going to exist also always in the fuzzy case. The drawback of this definition is that it's very difficult to compute the level sets of, in general, in an equation. To make a computation is very difficult with this notion, which is one of the most generals at the moment. So why using differential inclusions approach? So the idea of differential inclusions, well, here I have written for the case of n-dimensional. The advantage of differential inclusion is that when you are applying this approach to a fuzzy problem, you don't need the notion of differentiability for functions with fuzzy values, because all the derivatives that appear there are classical ones. So this derivative is not a derivative under the cases of the previous definitions. This is classical derivative. So it's much easier to compute. For the fuzzy case, what is made is, of course, we are going to cut again in levels for each alpha. You get a family of differential inclusions. These derivatives are classical. So in the linear case I wrote before, it is trivial to write the expression of the solution. And you have only one solution, the same solution, for the three problems that were written. I mean, we don't mind if the term is on the left or on the right. All these problems, which are equivalent in the classical case, are going to have exactly the same solution from the approach of the differential inclusions. So at first, it's simpler. It's simpler. It can be used also in nonlinear problems, of course. So one question when using differential inclusions approach is, okay, you have a problem in fuzzy sets. You are going to cut and have a family of differential inclusions. You are going to solve quite easily many problems for each level. But now, are you able to put it together, all the intervals, and get a fuzzy solution? So Phil Diamond, in a work published in Transaction and Fuzzy Sets and Systems, gives the sufficient conditions for this to be fulfilled, which are basically a boundedness condition about these functions f. And another hypothesis, which is called regular quasi-concavity, about decreasing character in the level alpha of the intervals, and good properties about how the intersection of the values of at a sequence of betas converging to a fixed one holds. So it is, we have sufficient conditions in order to guarantee that all these levels are glued together with good properties. No? So in some previous works made by Hallermeyer, Diamond, Kaleva, this approach was only used for equations that are obtained fussifying a real function. I mean, using Sade extension principle. So if this is the case, it is quite simple to use differential inclusions approach in the sense that the levels of the f are going to be the image of the real age of t and the levels of the element, the alpha level of the element. So just using the endpoints of these intervals, if the h has good properties, we can compare the solutions from differential inclusions approach with the 1 and 2 solutions. For example, if h is non-decreasing with respect to the second argument, what we call the solution from differential inclusions approach and the solution from the h-different approach are exactly the same. If h is non-increasing with respect to the second argument, what we have is the differential inclusion solution is the same as the two solutions. So if we have an approach which is simpler, and in some cases is the same as the 1 and 2 solution, it is better to use this approach. Many authors say that it is important to keep on working on the fuzzy differential equations from the point of view of generalized differentiable functions. Because it is said that you can select a type of derivative that can be more similar to the behavior expected in the process. I mean, if you have a process where it is supposed that the fuzziness is going to be less in time, okay, let's take to differentiability. No? So choosing a proper definition of generalized differentiability, you can adapt better to the properties of the phenomenon in question. Okay. But if you have an approach which gives the solution in a simpler way, and you know that it's going to be the same, exactly the same as the 1 or 2 solutions, it is better to use this approach. The problem in these results is that they are only valid for problems that come from the application of Sade extension principle. And if you consider just the simple problem of before, this is not true. This is not true because of this term. Because if this P is fuzzy, it's impossible to write this problem as a problem coming from Sade extension principle from a classical problem. So we have to check specifically what happens in this and other more general cases. So what we have found about this approach on this specific linear problem is that, first of all, the solution is simple to write. It's easy to deduce that. If the coefficient A is positive, we are in the case, it is the same idea of h non-decreasing in the second variable, but this problem does not come from Sade extension principle. But in any case, the differential inclusion solution is the same as the 1 solution also for this case. If A is negative, the other result is not extended. I mean, the solution from differential inclusions approach is not the 1 solution nor the 2 solution. What happens with the 1 and 2 solution? In general, independently of the sign of A, what happens is that the 1 solution is going to have non-decreasing diameter. The 2 solution is going to have non-increasing diameter. The differential inclusion solution is always in the middle. It's always in the middle. I mean, it is more fuzzy, it's fuzzier than the two solution, and less fuzzy than the one solution. And the identity is only possible for real cases. So since I don't have a lot of time, I will make a summary of it. The ideas were written here. So the differential inclusion solution is always in the middle. The one solution has increasing diameter, the two solution has non-increasing diameter. And the other is in the middle. The two solution has a problem. Since the diameter is non-increasing, it could happen, in many cases, that the branches, if you make a picture similar to what I've made before, the branches in T, they can meet. If they meet and cross, the two solution does not exist anymore. Even if it doesn't exist, it is still true that the branches are also inside of the region determined by the solution from differential inclusions approach. No, even in that case, it is not a good definition. It's not a solution, a two solution anymore, but that is the case. And the coincidence is only for real cases. The approach of differential inclusions, if we want to know if the expression of differential inclusions is the same as one and two solutions for the same problem of other problems, that's something I will tell you at the end, you are going to be worried about the monotonicity of the diameter of the level sets. Because the property that is sure is that one solution is going to be increasing diameter and the two solution decreasing diameter. So let's take the solution from differential inclusions approach and check the monotonicity of the diameter. And one of the questions that arises is, are the switching points always at the points where at the critical points of the diameter function? Because those are the points where the monotonicity changes. It's equivalent. It is not equivalent. That is not true. The critical point of the diameter in the differential inclusions may happen before the switching point or after the switching point. Of course, because sometimes you decide where you establish the switching point. And that is because the coincidence with the one and two solution only happens basically, except in the A positive, in real cases. So in general, it's in the middle. So the monotonicity may change independently of where you put the switching point. I have a picture here about this situation. In this case, the critical point of the diameter of the solution happens at the logarithm of 2. But the two solution would be well defined until the value 1. So this is one of the support, I think it's represented here. This is the two solution. This in red, you have the differential inclusion solutions. You see there is a critical point, there is a change of monotonicity of the diameter. And the green one, that I don't know if it is possible to see it very well, it would be the one differentiability. And here we have another example with A of t minus 1, which is the case where you don't have the one solution or two solution. And in this case, the critical point of the diameter, I think I wrote it here, it's before, in this case, the place where the two solution finishes is before of the critical point of the diameter of the red solution, which is the differential inclusion solutions. Okay, so another reason, as told before, about the periodicity, since there are not many, there's not many time, I will just say some ideas about the rest. If you want to use generalized differentiable solutions, and you want to model a periodic phenomena, you need to use switching points. You have to decide where are the points where you are going to switch the type of differentiability. And the calculations and the computation is not very simple. However, well, I have here the expression of the solution, the explicit expression of the solutions for some linear problems, which are very simple, and results that just by checking, by controlling the diameter of the forcing term, of the level sets of the forcing term, also considering the coefficient A, it is not difficult to prove the existence of periodic solution, but it's not, it is based really on an application of a fixed point result. It is not possible to do it explicitly. However, this is one example I have here. However, from the differential inclusions approach, it is very simple to check the periodicity. What we understand by periodicity? We understand that the attainable sets, we are going to start in a collection of initial points and let the flow is going to be determined, what is called the attainable set, is periodic. It is much simpler to study conditions that guarantee the periodicity of the solution from the differential inclusions approach. I have here some examples where we have not the periodicity of the solution, only the periodicity of the diameter, in this case. But if the coefficients A and B are periodic, and we have these relations between the branches of the initial condition and the forcing term, we are going to be able to prove if A and B are T-periodic, the solution is periodic, much more simpler than the other result. So periodicity is a phenomenon that can be modeled through the approach of differential inclusions better than using a generalized solution. Here we have an example where, of course, A is 0, B is 2 pi periodic, so the differential inclusion solution is going to be periodic, and here with periodic A and B also we see that the solution is periodic. And it is quite simple to classify properties that say that assuming that some of the terms are periodic, the solution is periodic. Assuming the solution is periodic, we have the periodicity also of some of the terms. It is quite easy to make a list of properties about this. And one last thing that we have recently found is, okay, the differential inclusions solution is simpler. It allows to study periodicity better. We don't need very complicated expressions to calculate the solution to simple problems. But in some cases, it is a one solution of the problem. In some cases, it is the two solution, if it is real many times. But is there any stronger connection between the differential inclusion solutions and the generalized differentiable solutions? In linear problems, it's very simple to explain it. And what we have recently found is that, do you remember at the beginning we put here some problems which are equivalent in the classical case? These three problems. These three problems under generalized differentiability have solutions that differ a lot, have very different properties. From differential inclusions approach, the solutions are exactly the same to the three problems, because the derivatives are classical ones. So you are reducing a problem to a classical ones using the endpoints of the B, really, and the initial condition, but it is much simpler, and the three problems have the same differential inclusion solutions. Okay, if you fix this problem, for example, well, any of them, and you calculate the differential inclusion solutions, the differential inclusion solution is going to, you can classify the intervals where the length, the diameter is non-decreasing and the parts where it is non-increasing. It's clear to do that, very easy. And you find that it is not necessarily the one solution or the two solution in all of them. But it is easy to check that the differential inclusion solution can be recovered completely by using one and two solutions of the three problems together. Instead of fixing one, if you consider different problems that in the classical case are equivalent but not in the fuzzy case, and you take the differential inclusion solutions, all the solution is going to be recovered by considering one and two solutions of these different problems. So this, as a summary, is a collection of reasons that make it easier, straightforward, not only for linear problems. I have illustrated with linear problems, but also with nonlinear problems, that the differential inclusions approach is a quite nice way of studying this kind of problem. So sorry if I pass the time. Thank you very much for your attendance and your attention. Thank you very much. Thank you, Jesus.
Thank you for your talk. And when you are studying the T periodicity, you are thinking about that we are in the fuzzy environment. So it's not very restrict. You think about preserve the periodic functions?
To preserve
sorry, yeah.
Periodic functions in what sense?
Well,
in the solution?
Yeah.
From differential inclusions approach is quite direct, in the sense that you only have to check just 3 conditions. I mean, the periodicity, the classical condition on the periodicity of the linear coefficient, the forcing term, the branches in this case, and just this thing, because with these 2 identities, you have that the attainable set, the alpha attainable set at 0 and t is the same, and the periodicity of the coefficients then force the periodicity. Instead of making a very tricky construction, in the differential inclusions, I don't know if I'm answering the question, of there is some detail more that you would like to know.
No, I'm thinking mainly that, well, as you know, in the fuzzy environment, everything is not crisp, it's no. Fuzzy. And,
yeah,
and
well,
when you are, suppose some T periodic function, so you need to satisfy one equality, some crisp equality.
Yeah.
In some moment must be the same value.
Yes, for all the alpha it has to be fulfilled.
Yeah,
it gives some variability because the branches of Y0 are not necessarily the branch. The difference between alphas is not necessarily the same as in the B, but well, in this expression they are linked. It has to be fulfilled for every alpha. Yes, of course.
Yeah. So maybe interesting to think about consider some similarity relation.
Mm-hmm.
Some similarity relation instead of the equality has a resolve from which we have the equality. So you are reducing the first equality, crisp equality. So I think that it could be also interesting to consider similarity relations for in this equation.
Okay, good idea.
In order to has a weaker definition.
Good. Thank you for the idea. We have not. We have just checked with the identity, but nice idea.
Yeah, because we are studying or we are using fuzzy sets, but with crisp restriction as the sum, the equality, and so this is why we have 3 different cases.
Yeah.
When in the crisp case we only have one.
You only have one. Yeah.
We are merging crisp and fuzzy notions. This is the most difficult sense here in fuzzy differential equation. We are considering crisp and fuzzy definitions.
But even in the interval is, for many of these issues, is very interesting also the crisp case. But you're right, in the fuzzy case you have to control all the alphas together at the same time. It's more complicated. So if it is possible to work just with the crisp case in some situation, it is simpler, but so it's a nice comment. but I'm sure it is interesting to make a deep thought about it.
Thank you again for your talk.
Thank you, Jesus. Thank you.
Any more questions? Okay, then let's thank the speaker again for the nice talk.
Thank you very much.